So if you recall, previously we were discussing some of the synchronization mechanisms that are part of Java. We talked a bit about things like the low-level atomic operations, compare and swap, the Java unsafe class, a little bit about the atomic, I think it was atomic Boolean class, and those things are all important to understand for the next programming assignment. What I'm going to talk about now is also related to the next programming assignment, or the current programming assignment, and that is the concept of semaphores. So this is a multi-part lesson that will give you hopefully all you need to know about what semaphores are and how to use them effectively. So we'll start off by discussing what is a semaphore, kind of conceptually. I'll talk about two common types of semaphores, counting semaphores and binary semaphores. I'll reiterate the human known use of semaphore. You probably remember that from last time. And let's start off with an overview of semaphores. So what is a semaphore? So conceptually, leaving aside implementation details, which we'll get to later, a semaphore is an object that can be atomically incremented and decremented to control access to a shared resource. And originally, semaphores were used to control access to shared railroad tracks. So if you take a look at railroad technology circa 1870 or something like that, when people wanted to share a track, they used semaphores, which are essentially signal flags, in order to indicate whether or not the track was unused, in which case it's clear, in which case someone can use it. But once someone goes to use it, then of course the track is in use, so the flag changed to stop. And naturally you have to get this right, otherwise you'll have two trains trying to be on the same track at the same time, and chaos and insanity will ensue. Concurrent programs use semaphores in order to coordinate the interactions between multiple threads. So I'll give you an example here. And in this case, we're going to have, we're going to share bottles of wine, and you'll see why in a minute. And in this case, we're going to have, multiple threads or beings or whatever who want to access the limited numbers of resources. So we're going to use a semaphore in order to be able to let the threads coordinate their access to these limited resources. So we'll start out with a count, which is called the permit count or the permit level. And this indicates how many units of a resource are in fact available. So we'll start out with 3 because we have 3 bottles. And when someone comes along and wants to use a resource, then atomically the count is decremented by 1, and whoever got access to the resource now has the ability to do whatever they need to do, drink the wine or whatnot, and they don't have to worry about running into problems by having someone else try to share it at the same time. So another thread may come along, may get another bottle from the resource pool, and at that point now, let's assume we have 3 threads that are off drinking the bottle, and the other threads that come along, as you can see here, have to wait. They're stopped, they're blocked, and the threads that got the resource can do their thing. Now, the threads that are waiting can either block indefinitely, or they may decide I'm going to block for a certain amount of time, like a couple of seconds or whatnot. When a thread is done with a resource, it gives it back, and what that does is that increments the permit count atomically, making it available for some other thread to acquire it. And I don't know what happened to my beautiful slide. Oh, there we go. Here we go. So if you go and watch if you watch this video, you'll see why we're using Grateful Dead wine bottles. Okay, so that's basically the way to think about this, right? You're trying to acquire a resource, and there's a count, and every time you try to get it, if it's greater than 0, you can grab the resource, and the count drops by 1. If it's 0, you have to wait. There are 2 general types of semaphores that you need to know about. One is the counting semaphore. And a counting semaphore has a number of permits, where the number of permits is typically greater than 1. And this is defined by a counter with a very specific set of semantics relative to the value of the count of the counter. Now keep in mind that the way the counter works is it's atomically incremented and decremented. That's part and parcel of what we're about to talk about. If the count is negative, then that means there whatever the count is, let's say it's -3, that means there are -3 threads queued up waiting to acquire the semaphore. And of course, they can't actually acquire the semaphore until the count goes above 0. And in that case, however large the amount is above 0, that many waiters will be able to get the semaphore and automatically decrement it. So that's what negative means. 0 means there are no waiting threads. So if anybody comes along and tries to get the resource, they're going to block until the count becomes positive, no longer 0. And then the final state that's important here is positive, which means that there are no waiting threads. The count's whatever the count is. And if someone comes along and tries to acquire the semaphore with 1, or try to get 1 semaphore, 1 permit, then the acquire operation will not block the thread that's trying to get the semaphore. You could argue that they're really just sort of 2 states, positive and 0 or lower, but we'll break them up into three states just to make it interesting. Okay, so those are the semantics of so-called counting semaphores. Then there are also binary semaphores, and as the name implies, binary semaphores have only 2 states, either acquired or not acquired, or 0 or 1. So you could imagine if you were kind of down on your luck and you only had 1 semaphore implementation to go with the counting semaphore and then treat binary semaphores as ones where the count's 0 or 1. And so obviously if the value is 0, then you have to wait. If the value is 1, you can get it. We'll talk about examples of counting and binary semaphores later. So obviously you'll see that the Palantiri simulator app is going to use the counting semaphore model. And you can download that. You can download the instructions for your assignment here, which you already know about. And that's a counting semaphore, right? Because we are going to have the count of the semaphore be equal to the number of Palantiri that are available to be gazed at. And as the different beings take turns gazing, then usually if there are more beings than there are Palantiri, then there'll be some that are blocked waiting and others that will be gazing. And you can really literally watch that if you run the app. You can see what's going on at any given point in time. We'll also talk shortly about another example called the ping pong app, which you can download here to see the code. And this basically plays ping pong. It's still kind of a silly little app, but it shows the key point. And it uses a pair of binary semaphores. And the binary semaphores are used to transfer control back and forth, alternating between pinging and ponging. And I'll give you a little bit more overview of that shortly. We talked about this earlier. What's a human known use of a semaphore? I mentioned the beach volleyball that we used to play at Corona del Mar, where we have these courts and we have teams. And the bag of volleyballs is used to limit the number of teams that can concurrently play volleyball. Obviously, if you ended up with more balls than there were courts, you would have chaos and insanity as multiple teams, 4 or 5 teams would be trying to play on the same court. That might be kind of fun to watch, but it's not really how you're supposed to play the sport. Okay, so that's just a quick overview of what a semaphore is conceptually, not really looking into any detail, which we'll cover here in a second with respect to how Java does it. So now that you have a vague understanding of what a semaphore is as a concept, let's talk about how Java semaphores are structured, what their functionality is, and what are some of the key methods that they define. So Java semaphores implement variants of counting semaphores. They have a count, as we'll see in a second, and you can read about them here. You have a class semaphore, and it implements some stuff. Not actually all that interesting what it really implements. In particular, it doesn't implement any of the synchronization-related interfaces, which we'll talk more about those when we talk about reentrant locks and reentrant read-write locks. Under the hood, and this is actually kind of cool from a design point of view, and hopefully this will also bring together some of the things from your CS 251 class to what we're talking about here. The implementation of semaphores uses the bridge pattern. Now, you may or may not remember much about the bridge pattern. It's a very interesting structural pattern from the Gang of Four book. And basically what it does is it decouples a class's interface from its implementation or implementations. And in the general pattern, it's because you want to be able to vary the implementation without changing the interface. In the case of semaphores, Java semaphores, they do it so that fair and non-fair semantics, which I'll explain in a second, can be supported uniformly. And so the way this works is you have this class called the semaphore class, and you have an implementation, and the implementation basically can be either fair synchronization for semaphores or non-fair synchronization with semaphores. I'll explain that in a second. And every operation that's in the semaphore interface basically forwards to the appropriate implementation, either fair or non-fair. And it's the job of the constructor of the semaphore to make the right implementation. So it's just classic bridge pattern. The way this is implemented under the hood is by an implementation hierarchy, or so-called implementer hierarchy if you're using pattern nomenclature, which is handled by this sync object. So we have this thing called a sync. I'll explain sync in a second. And you have a sync field, and then there's going to be a sync class, which extends something called abstract queued synchronizer. Abstract queued synchronizer is a very powerful framework provided in Java that is used by a whole bunch of different Java synchronizers. And basically what it does is it provides locking for so-called FIFO synchronization, first in, first out. There's a whole pile of them, like reentrant locks, reader-writer locks, semaphores, some other stuff as well. And basically they all work by keeping a count of something and then being able to have first in, first out access to update or decrement the count atomically. And I'll talk about that later. It's a very cool framework. There's a really nice article that explains how it all works, but we don't have to know the details of it at the moment. So here's kind of the way things work under the hood. So there's a constructor called semaphore, right? And you can pass to it several things. You can pass a permit count, so you can give it an initial value of 8 or 1 or 0 or whatever. And then you can also pass in a parameter that's a Boolean called fair. And this is what dictates the semantics of the lock acquisition model. And this is also done for other synchronizers. So Java reentrant lock, which we'll talk about and which will be part of assignment number 2, is built with exactly the same pattern. So the way this works is it dictates whether we use fair or non-fair synchronization. Fair synchronization ensures strict FIFO access to the count. And what it does, I'll explain what that means in a second. What that does is it enhances or it enforces fairness at the expense of performance. What the heck does that mean? First of all, what does it mean to be fair, right? What's a fair semantic? When people go and wait in line, Xavier. Treat everyone equally, but what does that mean in the context of waiting?
Whoever got there.
Right. So anybody here ever travel to the UK? Okay, so if you go to the UK, much like the US, people there tend to queue. So if you have a line, if they're traditional British, they wait in a queue, and they don't barge, they don't cut in front of the line. How many people here have ever been to, say, Italy? All right, if you ever go to an airport in Italy, people do not queue, they bunch, right? So you're waiting in, I think other countries, India is probably the same way, right? You go to the airport, you're waiting in line, it's like they call the flight, everybody just rushes in there, and it's a big, sort of a scrum, right? It's a madhouse. So they're queuing cultures and they're bunching cultures. And in much the same way that we have the same idea with synchronizers. So when something is fair, what that means is the operating system and the scheduler and everything else that's involved in doing the implementation of these synchronizers, the semaphores in this case, will ensure that whoever got there first in line, is always the one to go next. Now that's fair, but it's not always very efficient for a variety of reasons, and it's sometimes hard to realize why until we talk a bit more about how stuff works under the hood. There's something else called non-fair, and non-fair emphasizes performance at the expense of fairness. So what non-fair does is it says, I don't really care what order they came in here. I'm going to pick the next one, which is the fastest. And that often has to do with low-level things like processor thread affinity, thread scheduling affinity. Whatever thread finished whatever it's doing and goes to acquire the lock, oftentimes that guy's cache is warm. It'll take very little time to give the lock to that thing. And so as a result, to make things faster, we just say, oh, well, whoever I see, I look up, the scheduler looks up, oh, I see you there, go, right? It doesn't really matter if it's been waiting in line the shortest. So that's the concept of non-fair. So there's fair and non-fair. By default, if you don't use the constructor that has the fair flag, if you use the constructor that has no fair flag, the default semantic is non-fair. And that's because the goal is to optimize performance over fairness. And only if you need fairness do you actually use fairness. Fairness is way slower. Like so many other things in life, if we want to be fair, that often penalizes things, right? And I will focus purely on computing here, but like let's say, well, I won't. I'll give you another example. Let's say you wanted to hire for a position. The fair thing to do would be to post the position, to let lots of people interview, and then pick the person who is best qualified by some criteria, right? But that might take a very long time. So another way to hire someone is to say, walk out, look down the street, the first person walks by, you have the job, boom. Or call up your uncle, or call up your son or your daughter or whatever. That would not be very fair, but it might get it done fast. So that's the way that the system does things, because of course the operating systems don't care about equality, they care about throughput typically. So if that's the case, we're going to go with non-fair. You can also have the semaphore be created with a given number of permits. This is what the initial count is going to be when the semaphore starts. You can see that that's another parameter that gets passed in here. This is really important to remember. The parameter that you pass to the constructor of a semaphore is not a maximum value. It's an initial value. And because of this, it's actually possible to keep increasing this value. And there's no harm in that, other than being confused and surprised by the fact that you don't get an error. But the initial value to a semaphore is not a max. It's just the initial value. And that's kind of weird. And you might, if you're confused, as I was when I first learned about this Stack Overflow article goes into some detail about why that's the case, why it works that way. In fact, even more bizarrely, you can give a negative value to the semaphore. You can give it -50 if you want to. Not often a very useful thing to do, but you can do it. And if you do this, then all threads will block trying to acquire the semaphore until one or more threads increments the value to be greater than 0. Again, it's possible to do that. There actually are use cases where this is handy. Rather rare, but it's possible. So another thing to remember about Java semaphores is that acquiring and releasing permits to or from the semaphore need not be fully bracketed. What the heck does fully bracketed mean? Well, what fully bracketed means is the thread that acquires it must be the one to release it. That's what fully bracketed means. And in some cases, certain synchronizers, like synchronized statements, the curly braces that you have where you say synchronized, say this, open curly brace, blah, 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 close curly brace. Those are fully bracketed. The thread that acquires the intrinsic lock must be the one to release it. Likewise, there are things called reentrant locks, which you'll learn about. Once again, the thread that acquires it must be the one to release it. With semaphores, that's not the case. You can do it that way. Your Palantir manager does it that way. But it's not required. And there's lots of use cases that don't need that. And we'll talk about one with the ping pong thread, where the thread that acquires the semaphore is not the one that releases it. And that, in fact, is important because otherwise they wouldn't be able to take turns. OK, so that's just kind of a conceptual overview of Java semaphores. Now let's kind of dive a little deeper and start talking about some of the Java semaphore methods. You'll see that there's a lot of methods in the semaphore class, most of which you don't normally care about. There are a handful that you care about a lot. And these are the key ones we're going to focus on. Acquire, acquire uninterruptibly, try acquire, and release. And as you'll see, all of these methods really don't do much themselves. They simply forward to the implementer methods, which are part of the whatever was set up by the bridge pattern implementation in the constructor to be either fair sync or non-fair sync. And the implementation of all this stuff is done by the abstract queued synchronizer framework. All right, so let's take a look at acquire. So acquire obtains a permit from the semaphore, and you can see what it calls is it calls acquire shared interruptibly with a count of 1. So that means I want to acquire, I want to get 1, or rather I want to increment the count of the semaphore by 1, and I'm going to do it in a so-called interruptible way. And all that means is if somebody were to interrupt that thread, and we'll talk more about thread interrupts later in more detail, if someone was to say to that thread, hey, please stop what you're doing and do something else, if you were blocked in acquire, that would cause an interrupted exception to be thrown. That's not always what you want. So the alternative approach is to use acquire uninterruptibly, which ignores interrupts. So you can see here, acquire uninterruptibly is going to call something different, and it turns out that this thing will ignore interrupts. So if somebody tries to interrupt this thread, sorry, Charlie, we're just going to wait, which is sometimes what you want, sometimes what you don't want. There's also something called try acquire, and this uses a non-blocking acquire, which obtains a permit, in this case of 1, if and only if it's available at that moment. So if there is a free permit, then try acquire will acquire it atomically. But if there is no permit, it won't block. It'll just return with a false value. And this is kind of bizarre. This is really odd. And there's actually a good explanation for this. But if you call try acquire here, even if you have the fairness property set to fair sync, try acquire will not honor the fairness setting, and it will barge in. It'll cut in front. Actually, it doesn't cut in the middle. It cuts in the front of the line, and it goes ahead and will grab that permit. So try acquire with no timeout will barge. And the reason it does this is purely for efficiency's sake. It's kind of bizarre. The semantics are a little odd. But the reason it does this is that under the hood, the way try acquire is implemented in the non-fair try acquire shared method in the abstract queued synchronizer framework is it simply uses a compare and swap operation. Remember, compare and swap is the low-level mechanism by which these synchronizers are implemented. And with try acquire non-fair, it will try to acquire that. It'll try to do the compare and swap. And if it succeeds, it's done. It's like, I got the resource, I'm out of here, even though that's unfair. And that's because it makes it way, way, way more efficient. By the way, there's sometimes some confusion. People think when they see the discussion about compare and swap, which we talked about last time, that there's an unbridgeable divide between compare and swap spin lock kinds of things on the one hand, and things that will park themselves and go to sleep if they can't get the resource on the other. And you could certainly do it that way, but the way things work in practice, especially in Java, is that many of the synchronizers in Java, especially if you don't put them into fair mode, will try to do the spin lock first. And if the spin lock succeeds, they're done. And the reason for that is it's really, really fast. There's almost no contention or overhead. In many cases, if the spin lock fails, then and only then will the synchronizer go ahead and park itself and go to sleep. So usually these synchronizers try to do something in a non-blocking way first, and if and only if they can't make progress, they go to sleep. And there's all kinds of variants that you can have that adapt. Sometimes things will spin for a little bit to try to get the resource and only go to sleep if the owner of the resource has gone to sleep, in which case, why bother spinning? Because you're not going to get access to the resource. You're not going to get the lock. If the owner is asleep, they're not going to release it. So the point is that there's this concept of adaptive spin locks, and even the non-adaptive stuff typically tries to spin or tries to do a compare and swap first. And the reason for that is that not blocking is way, way, way faster than blocking. So they try to do things that don't block as much as possible. Yes, Joe? Yeah, good question. We'll see later when we talk about the timed try acquire. So there's a non-time try-acquire, which is this one, and then later we'll see there's a time try-acquire. And if you do time try-acquire with a timeout of 0, then that will actually use the queue. So it's bizarre, right? So the reason I'm kind of raising this point is it's not entirely intuitive what the semantics are. So just be aware of the fact that try-acquire, even in the fair synchronization setting, will barge, which is bizarre. And you'd have to ask the inventors of this. You could ask Doug Lee why he did it that way. It was a little bit curious. I probably would have done something differently, but they chose it for a reason. It had to do with efficiency. Release increments the permanent count by 1. As you can see, it does release shared. And keep in mind that it's perfectly OK for the count to go above the initial permanent count. So if the initial permanent count was 1, and you say release, 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 then the count will go up to 3 or 4 or whatever. That's perfectly OK. It's not an error for that to happen. There's some other Java semaphore methods. These are not as widely used, but they're worth being aware of for the reasons we were just talking about. So some of these methods, like this one, this one, this one, and this one, can actually acquire or release multiple permits at a time. So you can acquire, 5 permits. That's kind of like, actually a good example is when they have Ticketmaster, right? There's some people who go to Ticketmaster and the second, Justin Timberlake or Lady Gaga concerts are announced, they go there and they buy as many tickets as they can, sort of atomically, and then they resell them on StubHub or whatnot. So the idea is you want to get a bunch of things in one fell swoop. And obviously, selling a seat for a concert, it better be an atomic operation, or you'll end up with multiple people trying to sit in the same seat, which would be a problem. So that's kind of a use case for acquiring multiple permits. And you can see you can do it either non-interruptibly, interruptibly, either non-blocking, and you can also release multiple permits at the same time. So those are some methods. Then there are also a bunch of methods, try-acquire methods, that take timeouts. So here, for example, is timed try-acquire, where you can give it a timeout and a time unit. Like you might say, wait for 1 millisecond, or wait for 10 seconds, or whatever. And oddly enough, the timed try-acquire methods, as I was just talking about with Joe, do in fact honor the fairness setting. So they don't barge, right? Go figure. So I might have done it the other way around, but they didn't. So that's the way it works. OK, so that's the end of a discussion about what Java semaphores are. What we're going to do in a second is we're going to talk about how to actually use this stuff to write real programs.